Alright, in this video I'm going to make I'm going to do a problem where I have some ice and some water that have been put together. And what's important about this problem is that the ice is going to melt, and we're going to take that into account while finding the equilibrium temperature of the two substances. So first things first, 20 grams of ice at minus 10 degrees Celsius, and we're adding that to 500 grams of water at 20 degrees Celsius. The 20 grams is pretty small, so what we're going to assume is that all of the ice will melt in this process. So this ice is going to turn into water, and then the two sources of water are going to come to thermal equilibrium. We'll talk about, as we're going through the calculation, where we would notice if there wasn't enough energy to melt all the ice, and we'll talk about that at that time. But for now, we're just going to move ahead as if there is. So what we're going to do is we're going to find the energy required to raise the temperature of the ice from 10 degrees up negative 10 degrees to 0 so that it's prepared to melt. Then we're going to find the energy associated with the state change. Using those two energies, we'll find the total energy that was required to get the ice to water, and then we'll do the thermal equilibrium problem with the 0 degree water and the what's currently 20 degree water but won't be by then. So first of all, how much energy is required to take it from negative 10 degrees to 0? Have to convert my mass to kilograms. Specific heat of ice is given there. Careful, it's not the exact same as water. And a temperature change from minus 10 to 0 is a temperature change of 10 degrees. So that works out to, I think, 406, but let's just check. Yep, 406 joules. And now the ice is up to 0 degrees, so now we can melt the ice. Again, in kilograms. So I'm getting 6,880. Oh, I gotta be careful here. I miswrote that. It should be 334, which will make this 6,680 joules. So that's the energy required to melt the ice. So to get the negative 10 degree water all the way up to, or ice all the way up to water, is going to require 7,086 joules of energy. Where is that energy going to come from? Well, it's going to come from the 20 degree water. So let's figure out when that 20 degree water supplies the energy to melt that ice, how much it loses temperature, or how much its temperature decreases in that process. So it will lose the 7,086 joules of energy, and that will occur, or that will cause a temperature change. The mass of the water is 500 grams, so converting it to kilograms, I'll make it 0.5 kilograms. The C for water, 4,179 joules per kilogram degree C. And our temperature change is what we're going to find, 7,086. I got a temperature change of 3.4 degrees. I get that by dividing both sides by all this stuff. Anyway, okay, so if the temperature started at 20 degrees Celsius, and it lost 3.4 degrees, then by the time it's given enough energy to the ice to cause it to come up to temperature and melt, it's gotten down to 16.6 degrees Celsius. So that'll be its initial temperature in the thermal equilibrium problem we do last. I discussed that I assumed at the beginning that all of this ice was going to melt because 20 grams is a pretty small amount. If all the ice hadn't melted, then this number could have been greater than 20 degrees. And if it was, what we would have known is it would have used up all that 20 degrees before it managed to melt the ice. So let's say this number, just for the sake of argument, had been like 25 degrees Celsius. So it would have gone 20 minus 25, which would be -5. We know that water is not actually going to go to -5 degrees. What that would tell us is not all of the ice melted. That being said, that didn't happen, so let's forget about all that and do the thermal equilibrium problem. So here, we're going to have heat gained by the 0 degree water and heat lost by the 20 degree water. The 0 degree water has a mass of 0.02 kilograms. There's not very much of it. Now it's heating up just like water, so it's going to get the same specific heat capacity. And we know that it is going to go to some equilibrium temperature. We don't know that value yet, starting from 0. On the other hand, the water that was water all along, the 20 degree water, is going to lose an amount of energy. There's 500 grams of it, or 0.5 kilograms, same specific heat capacity. And here we start from some unknown we start from 16.6 degrees, and we're going to that same unknown thermal equilibrium. A little convenience here to make the math a little easier, because the specific heat capacity on both sides is the same, I can cancel it out and ignore it. 0.02 T then on this side, minus 0, so it's just 0. Negative 0.5 T on this side. And the two minuses make a plus, 8.3 degrees Celsius. Bringing this over, I get 0.52 T is equal to 8.3 degrees Celsius. And dividing both sides by 0.52, I can come up with that equilibrium temperature. And I get 15.96 degrees. So, we took the energy out of the hot cup of water to melt the ice. Then we allowed the two sources of water to come to thermal equilibrium, and the final temperature of the mixture is 15.96 degrees.